In this lecture, we are going to look at the pumping lemma for regular languages. Now, before we get to the pumping lemma, let's have a look at an example. We've already intuitively argued that the language L, consisting of words of the shape a to the n, b to the n, is not a regular language. Now let's prove this formally. So, for contradiction, assume that the language L would be regular. If so, then there must be a deterministic finite automaton that accepts the language L. Now, it's a finite automaton, so it has a finite number of states. That means if we start in the starting state and we keep reading A's, so we read A, and so on, at some point there has to be a repetition of some state. Because we have a finite number of states, we cannot get new states all the time. At some point, some state has to repeat. So we have a path in the automaton of the following form. From the starting state, we read k times a, we get to a state q. We continue reading l times a, and we get back to the state q. Such a repetition must exist because the number of states is finite. Now, what happens if we're on q and we actually continue reading b's? So we are looking at these two paths in the automaton now. We have already said that from the starting state, if we read k times a, we get to state q. And now we continue reading k times b. And this brings us, so from q, reading k times b brings us to a state q prime. Now, what do we know about q prime? Q prime is reached when the automaton starts in the starting state, reads k times a, followed by k times b. So it reads the input a to the k, b to the k. A to the k, b to the k is in the language of the automaton, so this means q prime must be among the final states, because this word is accepted by the automaton. Now, however, instead of reading b to the k after a to the k, we can also start reading b to the k after having read a to the k and a to the l, because after reading a to the k, a to the l, we are also in state q, just the same q as here. So, if we read b to the k from state q, we already know we get to state q prime. But now we have read more a's before this b to the k pass. So actually we have read an input word a to the k, a to the l, b to the k. So we've read the input a to the k plus l, b to the k. And this word is not in the language L, because a to the k plus l contains more a's than b to the k. So it's not of the shape of the words in the language. So what does this mean? If we read a to the k plus l, b to the k, we end up in q prime. So we can conclude that q prime is not a final state, because this word is not in the language. But now we have derived the contradiction, because we have derived on the one hand that q prime must be among the final states, because a to the k, b to the k brings us to q prime. On the other hand, q prime cannot be a final state, because also a to the k, a to the l, b to the k brings us to q prime. So we have a contradiction, q prime cannot be final and not final at the same time. So we can conclude that the language L cannot be regular. Our assumption must have been wrong. The proof that we've just done can be generalized to establish an important property of regular languages, the pumping lemma. So for every regular language L, we have the following property. There exists a natural number m, such that for every word that has at least length m, the word w can be split in three parts, a prefix, a middle part, and a suffix, such that x, y together have at most length m, the y, this middle part, is non-empty, and no matter how often we repeat y, so we can repeat it 0 times, 1 times, 2 times, 3 times, it does not matter how often we repeat it, we always remain in the language L. This is called the pumping property, because you can think of repeating y as pumping y. So in particular, we could repeat y 0 times. If we set I equal to 0, then we get just the word xz. So it follows that xz must be in the language L. Also xyz must be in the language L, but it's clear we started out with w being in L. We can also pump y twice, then we get xyz must be in L. We can pump it 3 times, then we have that xyyyz is in L, and so on. So when using this pumping lemma, you have to be careful about the quantifiers. The pumping lemma, it guarantees that there exists some natural number m, but we don't know which it is. It guarantees that every word that is longer than this unknown m can be split in parts x, y, z, but we don't know how this word is split. So we don't know anything about x, y, z except that x, y has at most length m and y is non-empty. So for some way to split it with these properties, it holds that however we pump, we are remaining in the language. So I hope that this pumping lemma will become more clear when we see some examples. Actually, the pumping lemma is easier to understand if you see the proof, because the proof is actually quite simple. If we have a regular language L, then there exists a deterministic finite automaton that accepts precisely the language L. So let's assume that M is this deterministic finite automaton that accepts L, and M has M states. So our automaton has M states. Now, if we read a word W that is at least as long as M, then the path through the automaton when reading W looks something like this. So this is not the entire automaton. This is now the path through the automaton when reading W. Why does the path look like this? The path looks like this because if our word W has at least length M, then we are visiting M plus 1 states in the automaton. And visiting M plus 1 states in an automaton that has only M states means that at least one of the states must be repeated. So we must have a loop along this path. And this is exactly what is shown here. So we read W, we have some prefix. Then we have our first repetition of states. And this means that there's some state Q. And then we continue reading, and after a while we get back to Q. It does not mean that this is a single transition. This is a path consisting possibly of multiple transitions. And after this loop we continue, and possibly there are more loops, but we are not interested in them. We are only interested in the first loop when reading W. So this gives us a decomposition of W into X, followed by Y, followed by Z. So this gives us this decomposition into X, Y, Z, where Y is the part of W that we have read on the loop. So we've started in some state, read Y, and gotten back to the same state. Now what do we know about X, Y, Z? We know that the length of X, Y together is at most M. And we know this because if we are reading a word of length M, we are visiting M plus 1 states, and we know that there must be a repetition. So among the first M letters, we must have a repetition. Now, this loop must consist of at least one letter. So it has at least length 1. And if we have such a loop, so we are starting from a starting state, ending in a final state, and we have such a loop Y on the way, then we can repeat Y as often as we want. It just brings us from a state back to the same state. So we could also just read xz, and xz is accepted. We could read y once, and we're still accepting. We could read it twice, 3 times. No matter how often we go through this loop, we always get a word that is accepted by the automaton. So every word of the form x, y to the power I, z must be in the language of the automaton. Now, the tricky part here is that we know that the automaton has some number of states m, but we don't know what automaton. So if you're speaking about an arbitrary regular language, then we don't know what the automaton is, and actually we will use the pumping lemma to show that languages are not regular. So we cannot assume anything about the size of the possible automaton. If we want to show that something is not regular, we have to show that no automaton can exist. So we have to show that this holds for whatever automaton m is, so whatever number of states this automaton has. And also, we don't know how this automaton would possibly look, so we don't know how this path through the automaton looks, and therefore we don't know how this decomposition into x, y, z would look like. So again, we are going to use the pumping lemma in order to establish that certain languages are not regular. Now let's do the exercise and let's show, using the pumping lemma, that the language of palindromes is not a regular language. So L now is the language of all words over AB that are a palindrome. So this means that the word is equal to its own reverse. Now, assume that this language was regular. If it was regular, then we could apply the pumping lemma. The pumping lemma then guarantees that there exists some natural number m, such that every word that has length at least m can be split into x, y, z with these properties. Now, we have to pick some word longer than m, but we don't know what m is. So how do we pick a word in the language that has length at least m? So this word must depend on the parameter m. So what palindrome could we pick that has length at least m? One such palindrome, for instance, could be a to the m, b, a to the m. This word, no matter what m is, always is a palindrome. And it always has length at least m. Okay, so the pumping lemma guarantees us that this word can now be split into parts x, y, z, such that x, y have at most length m, y is non-empty, and no matter how often we repeat y, we always remain in the language L. So no matter how often we repeat y, the word will always be a palindrome. Now, can this be the case? What do we know about x, y, z? We don't know much. But we know that x, y together has at most length m. And x, y together form a prefix of the word that we've picked. So x, y form a prefix of this word. They have at most length m. But that means that x and y must fall in this initial part that only consists of a's. So we may conclude that x only consists of a's, y only consists of a's because they are in this initial part of ma's, and we know that y is non-empty, so y consists of at least one a. Now what happens if we pump y? So for instance, if we pick I is equal to 2, so we repeat y twice. We pick x, y, y, z. The pumping lemma tells us that x, y, y, z must be again in the language. It must be again a palindrome. Is this the case? If we take x, y, y, z, then we increase the number of a's in this first part by k. So we get m plus k a's in the first part. So we get a word of the shape a to the m plus k, then a b, and then a to the m. But this word no longer is a palindrome. This word is not equal to its own reversal. We clearly have a b in the middle between the a's, but there's more a's in the front than in the back. So this word is not a palindrome, it's not in the language, and that's a contradiction to what the pumping lemma would yield. So where's our flaw? Our flaw is that we have assumed that the language would be regular. So we have a contradiction to our assumption of regularity. Our language cannot be regular, because if it was regular, then the pumping lemma would guarantee that this word xyz is again a palindrome. So we have a contradiction. The language L that we've started with, the language of palindromes, is not a regular language. If we want to prove that the language is not regular, and we want to show that this language does not have the pumping property, the property guaranteed by the pumping lemma, then it's not sufficient to show that it does not work for particular values of m, x, y, or z. The pumping lemma just says that there exists some m such that the pumping property holds. But we don't know which m, and it could be a very large m. It's not sufficient to show that it doesn't work for m is 2 or m is 3. We have to show it doesn't work for arbitrary m. And likewise, the pumping lemma just states that there exists some decomposition of the word w into x, y, z, so it does not suffice to show that there's some decomposition that doesn't work. We have to show that it does not work for all decompositions. So this is the statement of the pumping lemma. There exists some natural number m such that for all words longer than m, or at least as long as m, there exists a decomposition into x, y, z such that x, y have at most length m, y is not empty, and then for all I, if we pump the middle part y, I times, we remain in the language. Now if we want to show that this pumping property does not hold, we have to look at the negation of this formula. So what does this mean? If we negate this formula, then all the quantifiers are turned around. So we have to show that for all m, not just for particular m, for all m, there exists some word w, and this existential quantifier here is nice because it allows us to pick some word w, but this word w that we pick has to be at least length m. So it has to depend on the parameter m. Then again, there's a for all quantifier. We have to show that for all decompositions of w into x, y, z with these properties, so we cannot pick particular x, y, z, we have to show it holds for all, that there exists some I such that if we pump y I times, we get out of the language. And again, the existential quantifier here is nice because it means that it suffices to show that for a particular I, we get out of the language. So there's two parts where we are lucky. We can pick particular words. We can pick a particular word w that is longer than m. And we can pick a particular I that brings us out of the language. But there's two parts we cannot choose. That's the for all m and the for all x, y, z. These we cannot just show that it doesn't work for particular values. We have to show that it does not work for all possible values. Okay, let's do some more exercises. If we show that the pumping property does not hold, this can be also understood as a kind of game. So how does this work? We want to show that a given language L is not regular. So this for all quantifier means we have to show this for all m. Basically it means the opponent picks m. We are not in control of m. Some opponent player picks m. this existential quantifier means we are allowed to pick a word W that has at least length M. Now, it's again the move of the opponent. The opponent chooses the decomposition of W into X, Y, Z. But the opponent is forced to pick a decomposition that fulfills these properties, namely the length of X, Y is at most M and Y has at least length 1. And then it's again our move. We can pick an I such that if we pump the middle part I times, so if we take X, Y to the I, Z, we get out of the language L. If we can pick such an I, then we win. And if we can always win no matter what the opponent does, then we have proven that the language is not regular. So this game is only meant for helping understand how the pumping lemma works and how do we establish that this pumping property does not hold. Please do not use this argument in proofs. We will do more examples. In proofs, please argue the way we have seen already. So maybe one question as an exercise: who wins this game if the language L is finite? If the language L is finite, then always the opponent wins the game. And the move is very easy. The opponent can just pick an M that is longer than the longest word in L. So M is a number that is bigger than the length of the longest word in L. And then we are stuck at point 2. We try to choose a word in L that has at least length M, but there is no such word. So if the language is finite, then the opponent will always win. That means we cannot prove that the language is not regular. And that's also good because finite languages are always regular. So let's do some exercises. We look at a language consisting of words a to the n, b to the n for n greater equals 0. We have seen this language several times before and we have already proven that this is not a regular language. But now let's establish this using the pumping lemma. So for contradiction, let's assume that this language was regular. Then the pumping lemma would guarantee us that there exists a natural number m, such that every word of length at least m can be split into x, y, z with these properties. Now we can pick a word that is longer than m and is from the language. So what word shall we pick? If we want a word that has at least length m and is in the language, I think it's quite easy choice. We could, for instance, choose the word a to the m, b to the m. So we pick a to the m, b to the m. It's a word in the language and it has at least length m. And then the pumping lemma guarantees us that this word can be decomposed into parts x, y, z, such that x, y has length at most m, y is non-empty, and no matter how often we pump the middle part, we stay in the language. Now again, we don't know what this decomposition is, but we know that it has certain properties. So we know that x, y together have length at most m, and x, y form a prefix of this word. So just like in the preceding example, since x, y form a prefix, and this prefix is not longer than m, they must both fall into this initial part that consists only of a's. So x and y only consist of a's again, just like in the last example. And additionally we know that y consists of at least one a. Y cannot be empty, so k is at least 1. Now, what happens if we pump? Let's say that we take I is equal to 0. So for I is 0, we basically drop the y, we just take xz. What do we get? We get x y to the power 0 z, which is just xz. This means we remove this y consists of ka's. We remove ka's from this first part, so we get a word of this shape. A to the power m minus k, b to the power m. This word no longer is in the language because we no longer have the same number of a's as b's. We now suddenly have more b's than we have a's. So this word is not in the language L that we are looking at, and this is a contradiction because the pumping lemma guarantees us that it is in L. And again, where is the contradiction? The contradiction is that we have assumed that our language was regular. If this language was regular, then this word would have to be in L, guaranteed by the pumping lemma. So we may conclude that our language is not regular. Now we are asked to use the pumping lemma to show that this language is not regular. This language consists of words over the alphabet with the single letter A, and the length of the words is a power of 2. So it contains the words A, the word AA, the word AAAA. So the length of these words is the powers of 2, so it's 1, 2, 4, 8, 16, 32, and so on. Now, in order to show that this language is not regular, we assume for a contradiction that it was regular. Now, the pumping lemma would guarantee us that there exists some natural number m, such that every word that is longer than m can be split in this way. So what word from the language do we choose? I think it's obvious we will use m in place of the parameter k. So we choose the word a to the power 2m. So it's a word consisting only of a's and the length of the word is 2 to the m. Now, like in the exercises before, we know that this word only consists of a's, so we know that x and y only consist of a's, and the length of x and y together is at most m. So we know that x is of the form a to the j for some j, y is of the form a to the k for some k, y is non-empty, so k is at least 1, and x and y together have at most length m, so j plus k is smaller or equal than m. Now let's do some small computation. Since j plus k is smaller or equal than m, we also know that k is smaller or equal than m, and m is smaller than 2 to the m. 0 is smaller than 2 to the 0, which is 1. 1 is smaller than 2 to the 1, which is 2. 2 is smaller than 2 to the 2, which is 4, and so on. Now, since this holds, we may conclude that also 2 to the m is smaller than 2 to the m plus k. So this follows simply by the fact that k is at least 1. So if we add k, then we get something bigger. This smaller than follows because we know that k is strictly smaller than 2 to the m. And since k is strictly smaller than 2 to the m, 2 to the m plus k is strictly smaller than 2 to the m plus 1, because 2 to the m plus 1 is 2 to the m plus 2 to the m. Okay, so if we have a word that has the length 2 to the m plus k, then we know this word is not in this language, because it's between two powers of 2. It's between 2 to the m and 2 to the m plus 1. So it cannot be in the language L. How do we get a word of this length? We get a word if we pump the y once additionally. So if we take I is equal to 2. If we take I is equal to 2, we get the word x y square z. So we have repeated the y twice. Then we get a word of the form a to the power 2 to the m plus k. So that's exactly this length, 2 to the m plus k. And this is not a power of 2, so it is not in the language. and we can conclude that our language is not regular.